I'm going to be giving a little introduction about who we are and how we got here doing this talk. Um, First of all, myself, Will, and Sarah, we're all cavers. We were cavers before we were scientists. My background is in soil science. I've mainly worked in land reclamation, and none of that has anything to do with karst. I do also do some part-time work on karst projects in the state of Virginia. Then Will is a geologist, and he works full time for the Virginia Department of Conservation and Recreation in the Natural Heritage Program, in charge of all the karst, cave and karst studies, which means that these days he is as much a biologist as he is a geologist. And then Sarah is a geologist, and she has worked as a karst scientist in various capacities. She currently is the Springs Restoration Manager at the Sky Island Alliance in Arizona. Um, so we're also all involved with cave rescue, which is how we know each other, or at least how Will and I know Sarah, met Sarah. Um, and that's basically where our interest in CO2 and caves came from. So in particular, we had been attending the South Central National Cave Rescue Commission symposium in Bend, Texas, which of course Texas caves are notorious for having bad air. And the three of us would get to talking about carbon dioxide and had lots of questions, where's it coming from? Why is it so bad here? That kind of thing. And eventually in 2019, we were like, we really want to learn some more about this. We really should try to do some study while we're here. So we made big plans for the following year, in 2020, that we would do a bunch of carbon dioxide and oxygen monitoring in the caves that were being used, and also just do some polling with the participants in the seminar, asking them, kind of getting an idea about how they were feeling affected by carbon dioxide in the caves. And we were able to get that done in 2020, right shortly before COVID started shutting everything down. So we got a lot of work done that year. COVID did kind of derail us on some of the future work we wanted to do, but we're slowly picking away at it, and that is how we got here. I think the point being that in a way, this is kind of like a hobby study for us. This is not what any of us do in our real life daytime jobs. But we're interested and we're trying to learn about it. And we've also recruited people, a lot of whom are here on this webinar, who are also either volunteering personal time and resources to help, or who are working on this professionally and academically.
Okay, so everybody in here is an NSS member. Occasionally gets a copy in the mail every year or so of the American Caving Accidents Report, which is an interesting thing that's put out, and it's dependent on people submitting these reports to the editor. But it basically has a series of things that go wrong in caves. Most of the time, what you see in there, where there's actually incidents where somebody gets lost or someone gets injured or sick in a cave, and there has to be an operation for rescue. But sometimes people put in reports about close calls. And if you look at those close calls over the last 30 years or so, what you see is a pattern, one or two a year of people who run into bad air in caves. What you see on the screen here is just an excerpt from one of those reports. And, unless you're a really fast speed reader, no point to do that, to read the whole thing. But uh, what I want to point out here is that this story that they relate here is they are on September 1990 in a cave in Missouri. Three cavers are going to check out a virgin pit. Now, note this is not in Texas. And they're going to check this pit out, and they can see down a little bit, free climbing, climb down a little bit. They start feeling like they're really out of shape. They see a pit below the end of where they're climbing down that they're going to need a rope for. And but they start to suspect, well, maybe we're not all out of shape. Maybe there's bad air. Now, fortunately, these people were aware of what to do, if they suspected bad air, so they pulled out a lighter And they lit the lighter, and the lighter, or tried to light the lighter, it would not light and sustain a flame. They tried a few times. And then they said, well, maybe the lighter's not working. So they also had a carbide light, and the carbide lamp would not support a flame either. At this point, they concluded, well, we're in a low oxygen environment, and they exited the cave. But you see this kind of report repeatedly, and I'm sure many of you who are on this call have experienced bad air in caves and have similar stories.
So if you are a speed reader and read all the fine print in that last slide, you might have noticed that they make the reference to bad air, but they don't say anything else about the air. There's no mention of like what the problem might have been, other than that they talk about using the lighter, which would kind of imply um, a lower oxygen since the lighter won't light, but doesn't address why the oxygen is low, which is because some other gas is displacing or replacing the oxygen, and what the problem is from that other gas could be causing. So normal atmospheric air is going to be, we rounded a little bit just for simplicity, but 78% nitrogen, 21% oxygen, a little less than 1% of argon, and some other gases, and then 0.04% carbon dioxide. So basically anything that's going to affect that, lowering oxygen, increasing, and oxygen is usually going to, in the cave environment, this is most commonly going to be due to carbon dioxide, but could be due to some other gases. Um, but our focus here is looking at the carbon dioxide replacement. So first question then would be, where is this carbon dioxide coming from? And it is pretty well accepted that the majority of this carbon dioxide is coming from respiration in soil and epikarst. So as microorganisms are consuming carbon and oxygen and converting it to carbon dioxide, you're going to see lower oxygen levels, increased carbon dioxide levels. And in an ideal system, this is going to end up being, for every 1% oxygen consumed, 1% carbon dioxide is going to be produced. So it's this replacement reaction where carbon dioxide is replacing oxygen on a one-to-one basis. So if you look at the two numbers together, if this is all you're looking at, those numbers are going to add up to 21%. Because again, it's a one-to-one replacement. So if oxygen is 20%, carbon dioxide is 1%, 21%. And this is a figure that we adapted from an article by Shelley Burgle that was published in 2017. We're going to show the expanded version of it later, but on this adapted version, we just wanted to kind of highlight that respiration reaction that's going on. So just kind of showing a schematic of, you have your cave, soil at the ground surface, the epikarst, all that like bedrock surrounding above and surrounding the cave. And throughout that, you're going to have this microbial respiration taking place. So oxygen is going to be converted to carbon dioxide. You're going to have decreasing oxygen levels, increasing carbon dioxide levels, and then that enriched carbon dioxide air can move through fissures into the cave. Other air movement, you're going to see movement of air in and out of the entrance. That mass movement of air is referred to as advection, as opposed to in the soil where CO2 is just diffusing into the atmosphere from the soil. So again, the movement of air, that carbon dioxide enriched air from the epikarst, is typically going to be more of an advection movement of that mass of air in and out of the cave. And so this is trying to show here, again, we're looking at the replacement. For every 1% decrease in oxygen, we're going to have the 1% increase in carbon dioxide. So in the atmosphere or at the surface of, above the cave, we're looking at that 78% nitrogen, 21% oxygen, 0.04% carbon dioxide, and you can see it represented there, the oxygen and nitrogen with the big blue and green circles and then the little teeny amount of carbon dioxide. But then as you go with depth in the epikarst, you're going to start seeing the increased carbon dioxide because of respiration, decreased oxygen, nitrogen not really being affected. And as that carbon dioxide enriched air in the epikarst moves into the cave, it's going to be increasing the carbon dioxide levels in the cave.
So in addition to respiration and material coming through advection, that atmosphere coming into the cave and mixing with the regular atmospheric composition in the cave to produce a CO2 enriched environment. There's other ways. And now this is another way that I frequently hear cavers talk about, oh, it must be coming into the cave because it's degassing from water in the cave. So CO2 is getting dissolved somewhere else, being transported into the cave. And it's when it gets into the cave, it's like open up a beer can or something, and the CO2 is coming out under the lower pressure in the cave, or at least the lower partial pressure relative to carbon dioxide. So that is another way that the CO2 gets into the cave. And when we started looking into this, even before the stuff in Texas, I always thought this was the main mechanism, and I was surprised to learn, especially taking the measurements in the places we did, that even where there was water present, in a lot of the cases, the it appeared to have that O2 plus CO2 was 21% signature of respiration and not of degassing or replace or displacement, as we see here. You can see here a cave that we'll talk about more later. This is in a cave called Gorman Falls Cave down in Colorado Bend State Park in Texas. And where I'm standing taking these photographs is frequently 5% CO2 or higher. This day it was well ventilated, I think artificially ventilated for the training. It was probably about 3%. But you can see here this water that's very rapid flow coming across, turbulent flow coming through there. It's like shaking up the can of soda or beer or whatever. And you got all this surface area and fast moving water. And this is one place where we have pretty good evidence, as you'll see later, that we actually do have degassing going on in addition to the replacement or respiration. So another diagram like the one that Zena put up earlier, this one showing the end member of displacement. You can see here we have it come from a cave stream, sort of the Gorman Falls cave model. The CO2 coming from water could also be coming from drip pools, could also be coming from a static, phreatic lake or epiphrenic lake that's in the cave. But we just use the stream as an example here. But any kind of water that's coming into the cave that's enriched in CO2 relative to the atmosphere is going to lose CO2 to the atmosphere. Sometimes depositing speleothems as it does so. In any case, you can see here the CO2 is replacing not just the oxygen, but oxygen and nitrogen. So in a system like this, your CO2 rises not quite 5 times as fast as the oxygen falls. I was emailing with Dan Breeker, who helped me say some more about this later. He says that, it's more complex because some O2 goes into the water and there's, different rates of diffusion and things taking place. But, to a rough approximation, for every 5% rise of CO2, it takes that much CO2 rise to get about a 1% reduction in oxygen. And that's because it's really just displacing something if this was an isobaric system. And you can see here sort of the diagram that brings it together. It's sort of these two most common mechanisms. You have this displacement, the water that's coming into the cave is losing CO2 into the cave atmosphere. You have replacement or respiration, where that water or that air from the epikarst is advecting into the cave. And then, of course, you got advection from the cave entrance. You could also maybe call that ventilation from the cave entrance. That's going to be a function of a lot of different factors.
So just touching on that a little more about the some of these factors. Again, the entrance is going to have some control over how advection is moving air in and out. So, some caves have very tiny entrances. Some caves have great big entrances, and that, of course, is going to involve airflow. Some entrances get blocked. That is very much going to affect airflow. Next slide. And then also seasonal and weather effects. In the summer, much more active respiration is going to produce more carbon dioxide in the epikarst, which can result in more carbon dioxide in the cave. In the winter, less active respiration, and also thermal turnover is going to promote air exchange between the cave and the surface. So that those together are going to help lower carbon dioxide levels in the cave. And this photo is from the South Central Texas NCRC seminar a few years back. It is not uncommon that we get ice storms or snow while we're there. It's always held in late January, early February. The reason being that that is when the caves are most accessible as far as not having as bad carbon dioxide issues. Um, then also high pressure fronts can increase pressure in the cave relative to the epikarst, which is going to suppress advection and degassing. Low pressure fronts are going to do the opposite.
So, as we say, Texas is the Republic of Texas is the king of bad air. But there are a lot of other places in the U.S. In fact, most places people have looked, they have found caves with bad air. Some known locations with bad air caves have been reported to us: Arizona, New Mexico, Great Valley, Shenandoah Valley, and extended in Virginia, West Virginia, Maryland, Pennsylvania, Southern Indiana. There's been reports out there and some studies that were monitoring this going on. Missouri is the report in the NSS News. And then some more of the Western stuff out in Nevada. There's a couple caves with some significant bad air issues. There were some presentations about caves at Great Basin National Park at this year's National Cave and Karst Management Symposium, and they were talking about CO2 monitoring there. Of course, people who've been caving in Mexico and Central America run into this quite a lot in some of those caves, and European cavers are not averse to this either. There's even a lot of work been done on this issue in Australia, so it's really a global problem where we have caves and karst, but in some areas it seems to be more recognized and perhaps more prevalent than others. One of the things that we are trying to do, and it's a side project, like Zena said, is to accumulate data on the occurrence of high CO2 caves. And Zena's working to put together like a Google Forms thing where people can submit reports of CO2. Just don't quite have it working yet. But that would be something useful to sort of compile a database. I think a lot of times when we talk to scientists or cavers who haven't encountered it, they think it's an unusual problem. And it really isn't that unusual.
All right, so taking a little look at safety standards. Again, atmospheric air, we've got the numbers there, talked about those. Soil air and epikarst air, we're going to see lower oxygen and higher carbon dioxide numbers. And then looking at the like basic workplace safety standards, I'm going to jump down to OSHA. They implement an oxygen standard of 19.5%. So for your, on average, for your 8-hour workday, you have to be above 19.5% oxygen. And then they also have a 0.5% 8-hour, and again, weighted average. I'm just going to refer to the average, but this is like the, weighted average throughout the day. 0.5% carbon dioxide standard. The National Institute of Occupational Safety and Health also has recommendations for exposure limit. They define it as a 10-hour day, but the same number, the 0.5%. And since these numbers are pretty low, often you'll see the carbon dioxide expressed as part per million. So 0.5 would be 5,000 parts per million. They also have a short-term exposure limit. So this is a level that you wouldn't want to be at for more than 15 minutes. And they define it at 3% carbon dioxide or 30,000 parts per million. And then the immediate danger to life and health, they define as 4%. So this is like, 4%, you want to just turn around and leave. Yeah, so 4% or 40,000 parts per million. I did. Okay. I said, yeah. All right. So as far as health effects go, this is per OSHA, what they're recognizing as health effects. That again, like you should be good to 19.5% oxygen. That's their minimum acceptable level for a workday. And then they show 15 to 19.5% decreased ability to work strenuously, impaired coordination, early symptoms. So this doesn't really sound so bad. 15, this 15 to 19% range is kind of like you might be feeling it. You might have to work a little harder. Like, we don't think you should be working in this environment, but it's not going to kill you off. It's just going to, cause some deficiencies. And then like the 12 to 15% range is where things are starting to go south. And you can see the rest of it, but we're going to look more at those top few numbers. So the thing to keep in mind, if we're looking at the one-to-one replacement, oxygen, carbon dioxide, if we're looking at 15 to 19.5% oxygen, then that's going to be the equivalent of 1.5 to 6% carbon dioxide. So keep that in mind when we go to the next slide. And then, 12% is about where they're looking at like, you're really feeling bad to like things are really taking a turn for the worse, right? So 12% oxygen would be about 9% carbon dioxide. All right, now we're looking at elevated carbon dioxide symptoms, and this is from the USDA Food Safety and Inspection Service. And so they're recognizing that 0.5% for the OSHA 8-hour permissible exposure limit. They're saying at 1% carbon dioxide, typically no effects, possible drowsiness. We can tell you this is absolutely an understatement. Not to say that everybody's going to feel bad at 1%, but to say typically no effects is definitely an understatement. At 1.5%, mild respiratory stimulation for some people, 3%, which is that NIOSH 15-minute exposure limit, moderate respiratory stimulation, increased heart rate and blood pressure, and then the 4% immediate danger to life or health. 5% strong respiratory stimulation, dizziness, confusion, headache, shortness of breath. So all of this, like things are going bad at 5%, but by the oxygen table, you're still in pretty good shape. And then 8% dimmed sight, sweating, tremor, unconsciousness, and possible death. So 8% carbon dioxide, you might be dying, but on the oxygen table at 9% oxygen, or decreased oxygen, I should say, you're at the point that things are going to start turning bad. So the point here is that the elevation in carbon dioxide is causing more problems than the decrease in oxygen. Sorry, and also just making the note that sometimes these effects are delayed. So in the moment in the cave, you might be at these elevated levels and people are like, well, I don't really feel so bad, maybe just a little shortness of breath, but I can keep working, I'm good to go. And then hours later, they feel terrible. As far as the combination, looking at, both the carbon dioxide or elevated CO2 and decreased O2, we have not found any studies yet that talk about that. Again, high CO2 will produce severe effects before the equivalent low oxygen is going to be affecting you. We do like to make the point that high carbon dioxide caves are emphatically not like being at altitude. You'll often hear people say like, oh, the low oxygen is just like being at a high altitude, but it's not, because at high altitude, the relative concentrations of gases don't change. It's still 21% oxygen and 0.04% carbon dioxide. So at altitude, the partial pressures are lower, but they're similarly lower, as opposed to, what we're talking about where oxygen decreases, but you're having the effects from the high carbon dioxide. In healthy humans, the difference in carbon dioxide concentrations in blood versus the atmosphere is what drives gas exchange in the lungs. So if your lungs are full of carbon dioxide because you're breathing in high carbon dioxide, it's hard to have that CO2 get lowered in your blood, which means your blood starts to go acidic, and a lot of bad stuff happens at that point. So um, this is a slide from a graph from a study that was done in 2012. And this is really what caught our attention several years ago at the Texas NCRC seminar when DJ Walker presented this, because it's looking at the cognitive effects of slightly elevated carbon dioxide concentrations. And you can see these levels, 600 parts per million, 1,000 parts per million. Well, the white dots are showing 600 parts per million, blue dots, 1,000 parts per million, and the black dots are exposure to 2,500 parts per million. And just to remind you that that 2,500 parts per million is 0.25%, which is still only half of what's considered acceptable for a full workday. So this, basically they had a series of different cognitive tests. You can see those different categories at the bottom. But you can see that, for almost every single one of the categories they were looking at, there was a notable decrease in function as carbon dioxide was increasing. Um, Particularly looking at initiative, um, basic strategy, like those things declined significantly at that as carbon dioxide was increasing, but still at what would be considered relatively low numbers compared to the workday standard. So this really made an impression on us, because we're used to talking about carbon dioxide and thinking about like, oh, 1-2%, that's really high, that might have an effect on you. But now here's the study that's saying no, even at these low levels, it's having a significant effect on your cognitive abilities. And we're there for rescue training thinking, like, how is that affecting us? And like, how do we want to be doing this if we're not really thinking clearly? So we're not trying to be alarmist. I try to make that point. Like, we're really not trying to be alarmist. It's just really important to be aware that there may be more impact than we realized. So again, going back to, we in 2019 came up with, we want to do this big study. We're going to monitor carbon dioxide. We're going to be like getting people to tell us about what they're experiencing, how they're feeling, what are they noticing about other people. And, this was just a lot of interesting things that were reported. And this is just a small sampling of things that people reported. Uh, is their experiences throughout the week when we were in some of the higher and saying, maybe like 2% type environments. One of the side effects of elevated carbon dioxide that we've seen in some papers is anomic aphasia, which is the ability to recall words. So it's kind of like that. It was at the tip of my tongue. And we see that a lot. And I know people will say, like, but that happens all the time. And it does happen all the time, but it's happening. We felt like it was happening more than the normal amount of time that, people have this little like forget a word. So things like we were working on the litter and an instructor asked, can you pass me some of that flat stuff that we use to tie things? Because she was trying to get some webbing and she couldn't think of the word for it. I was trying to answer a question. I felt like I was thinking clearly, but I couldn't get the words from my brain to my mouth. It sounded like I was drunk. I asked a student about her involvement with rescue, and she told me, I do that thing where you walk around outside and look for people. And what she was trying to say was that she does search and rescue. Even though I had been unable to breathe properly, I didn't think it was a big enough deal to warrant getting out immediately. So again, kind of this like, just not really making the best decisions. And this one, the lighter wouldn't work at the bottom of the third drop, but we felt okay, so we stayed down there anyway. I felt sick all the next day and stayed at the lodge. And then we are all individuals. We are all going to respond a little differently to this. And being in Texas really emphasizes that to us. Particularly, I think a lot of Texas cavers kind of know what their carbon dioxide limits are. And we had some people who, if it was approaching 1%, like they knew they needed to get out, they'd feel nauseous, they know they get sick. And other people who would happily work at 5% if they were allowed to.
Okay, so when we're in the doing this study, and this starts getting into some more of the little technical part of it too, is how do we actually measure CO2 and O2 in caves? Well, what we use these days are handheld meters. Now, most folks who work in search in rescue, confined space, et cetera, they're used to a four gas meter. Unfortunately, four gas meters don't typically include carbon dioxide as the mix. It's carbon monoxide, hydrogen sulfide, hydrocarbon gases like methane, and oxygen. So you can get an oxygen reading with a four gas meter, but you really don't know what the CO2 levels are. So we started carrying CO2 meters, which over the last few years have become affordable. And as we'll talk more about later, I'm sure there's also custom meters being built by people. Um, Including at least one person on the call on the seminar today. So you can see here something maybe at CO2meter.com on the left. That's like about a $400 unit there. You can see the CO2 being displayed and the oxygen being displayed on the oxygen meter there. That's in a cave called Lemon's Ranch Cave down in Texas. One of the things we did talking about meters, I didn't know where to put this slide, so I thought I'd put it here, was we did compare some of these handheld units that caterers are building with commercially produced units. Now, at first glance, you see this and you see that the commercial unit represented by the black and the red here really seems to outperform these two examples of homemade units or caver built units. Um, and what we did for a test was we put them outside the cave. We knew a place in Lemon's Ranch Cave where the CO2 is reliably 4%, and it's very close to the entrance. So we put them in the pack, crawled into the cave as quickly as possible. So about 8 minutes later, we're in the 4% CO2 environment. Uh, we stayed there, let the meters run for a while. After about 10 minutes, we decided, well, we don't want to be here any longer. So at this point, you can see the commercial meter. This particular one is this Pro 10 by CO2meter.com. It's their replacement for the one shown in the previous slide. It reached that value very quickly and stayed there. And the others were starting to approach that value. When we came out, did the opposite thing. Um, Now, the big caveat here is that this CO2, this Pro 10 commercially available meter really isn't terribly cave worthy. It has large open vents on the back, which mud and dirt and vapor, water, whatever can get in and out of these things easily. So the guys like Jeff, who's on the call here, um, who makes these things, they put in a semi-permeable or gas permeable membrane that keeps out dust, helps keep out moisture, but allows gas exchange. The price you pay for that is that it slows it down. And it'll be when we get done with this the talk, I want Jeff to talk about some of his new work he's doing on both a new meter and also some loggers to measure CO2 in caves. Because these units are great, they're super durable, but you have to be aware if you're going to use one that you may be getting a delay. And if you start seeing a reading rise like this, it may be time to try something old fashioned like the lighter test. So the lighter test is what was referenced in that first slide, which if you're in bad air, the way to test for it's a lighter, which works great unless there's methane around. But let's just assume there's no explosive gases around for now. And this is the common thing that's been used in Texas. Bring your lighter with you. As long as the lighter lights, you're okay. If the lighter goes out, maybe not. So Gary Smith, who's an Australian caver, he's done a lot of work on this. I'll talk about Gary a little bit more later. But he had a lab study that he published in 96 that showed that a butane lighter would extinguish at 14.5%. Bush Frelia, a Texas caver, he earlier had said about 17% is where he observed them going out in Texas caves. Our work said 17.5%, pretty much 100% spot on with Frelia's work. And if you'll read back the Smith study, what you find out is that the other gas present to dilute the oxygen was argon. And in a real cave environment, here we go. Here's that theme again. It's not an inert gas, it's CO2 building up, which is a product of combustion. And that's probably increasing the minimum amount of oxygen required for combustion. So I would use the numbers that Fraulia got and that we confirmed as for rule of thumb numbers for what oxygen percentage you're talking about with a lighter test. We got a couple cool little videos. Okay, and you can see in that video that we're a little over 3% CO2, about 18% oxygen according to the meters. And we get flame, but the flame's kind of dancing around, behaving erratically.
Go. Mhm. Yep, yeah. Let's go back.
Hey, we're gonna call it, I think. Air's bad down here.
Go. Mhm. Yep, yeah. Let's go back.
Hey, we're gonna call it, I think. Air's bad down here.
Okay, so kind of a fun little side note on this. Not every caver wants to go out and spend $400 on a carbon dioxide meter. Cavers also tend to be kind of innovative. So one year when we were down, when we were, I guess in 2020 actually, when we were working on the well, no, in 2019 when we were planning working on this study, some people were sitting around discussing this and like, well, what are other ways that we could measure CO2? And there are a lot of attendees who also have an EMS background, and the idea is using these easy cap detectors came up. So what they are, if you're not familiar with them, are just a little device that gets attached to an oral airway when you're doing CPR on a patient. It gets attached in line between the oral airway and the bag for, blowing in the air. And it's measuring, it's looking at the air that's being exhaled from the patient. So if cellular respiration is going on and good things are happening in the body, then there is going to be CO2 present, just the way we exhale air. But if that's not happening, then CO2 is not coming out, and that's bad. So the way these work is that, it's basically like a litmus paper in there, that at atmospheric air, it's going to be purple. And with increasing CO2, it turns that yellow color. So when you're doing CPR, you want to see that yellow color because that's indicating that CO2 is getting blown off. So the question had come up like, well, is this something that we could use in the cave environment? If we just carry one around in a cave, is it going to change? And, people have used these for CPR. It's like you just use it and throw it away. You're not going to use it again. So no one really knew anything about them. Like if you just carry it around, what's it going to do? And how long do they last? And does it go back and forth between yellow and purple and yellow and purple? And, could you use this as sort of like a little monitor to carry around with you? So we thought we would check that out. So everywhere we went, we had our CO2 meter and our lighter and our oxygen meter, and we were carrying, and the reason we have a bunch of them is we were trying to see how long they would last. So every day we would open a new one. We got these from our rescue squad, and they were all either like just recently expired or like many years expired. So we were also kind of wondering like if they're many years old, will they still work? So that's why we have like a whole ton of them. But anyway, for the cave, we want to see them purple because that's indicating there's not high CO2. So you can see these examples where carbon dioxide was around 620, and so, just a little elevated, and they're all still pretty purple. And then on the right there, where the carbon dioxide is over 1%, and you can see them all, turning yellow, maybe not like the bright yellow, but kind of getting in that grayish purple to yellow shade. And they lasted several days, and they did walking around in the cave. We would, when we were in good air, they were purple and they would change pretty quickly and they'd go back and forth. And so, we're not saying it's better than carrying a CO2 meter, but it's better than not having anything. So, this is something that if you have access to them, just makes a nice little um, simple monitor that you can carry with you. And also they fail to yellow. So when they stop working, they're going to turn yellow. So it's going to be a safe fail in the sense that maybe you left when you didn't need to, but it's not going to fail to telling you that there's low carbon dioxide when that's not the case.
Okay. I just, by the way, I just looked at the chat and I didn't mean to ignore any thing that was in the chat. I think we'll address those when we get done with the presentation. But there's a couple good questions in there that people brought up. Looking here, this is actually but that week we also developed a relationship that Sarah Truby connected us, the group with Dan Breeker at UT Austin in the Breeker Lab that does carbon dioxide work he and his grad students have for years. Also, of course, Jay Banner and his students at UT Austin kind of do more of this work than anybody else. And we said, hey, would you be interested in seeing some samples from Colorado Bend State Park? And Dan's like, yeah, that'd be great. So we got some sampling apparatus from him and got some Mylar sampling bags, and we collected samples. You can see here, it's maybe 30 samples from across the Colorado Bend State Park caves that we were visiting during the rescue training. And this was in 2020, a month before the pandemic. Um, so what you can see here is this large graph. You have the decrease in O2 on your vertical axis and your increase in CO2 on your horizontal axis. So O2 decreases as CO2 increases. But the rates tell you a lot, as we alluded to in those little process cartoons earlier. The rates tell you a lot about what the mechanism, or the relative rates tell you a lot about the mechanisms that are involved. So Dan made these graphs based on their analysis. He and Natasha Saccone did the analysis. Natasha maybe ran most of the samples. Uh, and what you see here is these lines. You see the respiration graph alone, which is, 1-to-1. You see respiration plus diffusion because oxygen and CO2 diffuse at different rates. So it adjusts where this curve falls a little bit for the atmosphere. Then up top, you see what goes on right at the boundary where CO2 is leaving water. There's a little bit of oxygen that goes in. I've been talking with Dan Breeker about coming up with a curve that was or a line that was representing a combination of degassing and mixing in the cave environment. And we haven't been able to come up with an analytical one yet. It turns out to be a fairly complicated problem. So I came up with a very simple-minded approximation. This is just a straw man for approximately where that line is going to lie, where for every 5% reduction in increase in CO2, you lose a little more than 1% oxygen. What you see here in the top right, these are all the really low CO2 level caves that we sampled. Not every cave in Texas is a CO2 death trap. You come over here, that's all up here around the uh, the origin of the graph here. So it's over here, zero change in oxygen, zero change in CO2, very close to atmospheric. That's what all this stuff is. And I think a lot of what you see here is probably just because the values are so low that the analytical error becomes very significant. So I don't know how much credence to give to those values, except that, there was nothing all that out of the ordinary. You get to the higher values where we can get more interested for acute safety concerns. You can see that from about 1 till maybe 2.5, 3%, everything plots really close to that respiration plus diffusion line. Once you get to the really highs, getting over 3% CO2, something interesting happens. You suddenly see these points start to drift up, where you're gaining CO2 faster than you're losing oxygen. And one way to explain that is that you've got you know, allogenic, as Ira mentioned in the chat. You got CO2 being brought in from somewhere else, and then exsolving, coming out of the water into the cave air. So you probably have both displacement, or which would be degassing, and replacement or respiration taking place, reflecting the gas compositions towards the right side of the graph. Where this comes back to the safety, again, this was our main concern initially. We had to do with the very practical issue of not killing ourselves in caves. Is that where the lighter test, some of our traditional methods of evaluating gas mixtures in caves work. These samples out here on the far right, especially that WS13, when we took that sample, literally we were down at the bottom of the Gorman Falls cave and the lighter lit just fine. And we're well over the IDLH for carbon dioxide. So it is food for thought that when you start getting into these higher environments, maybe that test isn't as reliable as in every case. So there's a lot of research needs, both from a safety and, of course, from a science perspective, as we'll hear going forward. Really needs to be a broader investigation of just the occurrence, just a sort of an inventory of where elevated CO2 in caves is observed, and how severe is it, how prevalent is it, and what kind of variability, particularly seasonally, does it have. The things that folks at UT are working on is to better understand processes that produce these high CO2 atmospheres, particularly where is that CO2 coming from, which everybody's got sort of ideas, and we've been learning a lot about what we don't know, and a little bit I'm learning some things we didn't think we were correct before, like about the respiration. It's really interesting. Evaluate cognitive and physiological signs and symptoms for cavers exposed to elevated CO2. My stumbling over my words does not indicate that I am currently in a high CO2 environment, but maybe was exposed too much in them in the past. Also, this is where a couple folks on this call hopefully will have something to say. Develop technology for monitoring cave atmospheres in an affordable and efficient manner. We need better handheld meters for spot measurements. And that's where these custom caver built units that are ruggedized are really good. It's just coming up with a way to maybe improve that gas exchange a little bit so we get a little quicker response. Also, we need loggers. There's a few loggers out there. We've tried a couple of times with disastrous results. I know Matt Covington and his group at Arkansas have come up with some loggers, and I know Jeff Frank is working on a logger that would be useful. We tried the deploying of a Sala logger in Gorman Falls, and the water decided to rise and flood it and destroy it. So our one attempt there was unsuccessful. Bottom line from the lighter test is, if the lighter doesn't work, you should get out of the cave. If the lighter is still working, you have other symptoms, you still might have a problem, and you should consider having other sources of ways to detect high CO2.
So just a couple examples of things we looked at. This is the entrance to Gorman Falls Cave. It's a notorious high carbon dioxide cave in Texas that gets used for the seminar. They ventilate it for a couple days before we even try to enter it. So the cave basically has these three little drops as you're going in, and we rigged up tubing, which you can kind of see in that picture at the top. But basically, when the air was acceptable to be going in, we put tubing in that went down, one tube to the third drop, one going like halfway down the second drop, and then one that went down the first drop, so that we could later pump air and see what the oxygen and carbon dioxide levels were like. This is at the bottom of Gorman Falls. So this is where Will was showing, that we, wait, is there another slide with data, or did you already? Okay. So this is at the bottom of the cave where water's coming in. So, in addition to the respiration reactions, we're also getting degassing, um, pretty notable at the bottom of the cave based on the measurements we're seeing. Um, so this was, we basically were pumping the air. We had our meters in a little Ziploc bag, kind of like our little um, flow through chamber. We just pump air until they equilibrated. And here we had the oxygen reading 12.5%. The carbon dioxide meter was reading 4.7, but also the meter's limit is 5%. So we were probably kind of maxed out on it, that you know, we're sure the carbon dioxide was higher than what the meter was telling us based on the oxygen measurements.
Okay. So we're not the first people to look at this, as everybody knows. And I'm sure some folks there are saying, "Man, these guys are just reinventing the wheel," and we're doing it with a few different tools, maybe. But I do want to acknowledge some people who've done a lot of work in the past. Bill Elliott's one who comes to mind. He was, University of UT Austin in the 80s and 90s, and he's a biologist and conservationist, first and foremost. And because of that, going into caves for biological sampling, he was encountering a lot of high carbon dioxide environments. So he got interested, and he was using Draeger tubes to perform measurements of CO2. He also noticed in some of the caves, especially ones with a really high CO2, he was seeing uh, oxygen levels low, but the CO2 wasn't rising as high as the oxygen was dropping low. And he thinks in those cases maybe it was due to excess nitrogen in the systems, which is something that miners refer to as black damp because your light goes out and you can't see when they use carbide lights. But anyway, there are some weird things that take place at these really high levels, or really low oxygen levels. And maybe Miel Lee has seen some kind of suspiciously similar stuff in some of her work that hopefully she'll share when we get done with the presentation. So maybe something like that's going on down in Gorman Falls Cave, where we saw that CO2 level that didn't account for all the oxygen that was missing. So here's one of the classic Bill Elliott graphs. There's a cave called Gorman Caves, which is not to be confused with Gorman Falls Cave. Um, and this was a profile of CO2 levels and oxygen levels that Bill did during the year they built a cave gate down there to protect some hibernating bats and also a summer bat colony in Gorman Cave, which is right along the Colorado River there. But you can see here that in the open circles are in the fall, and that was the fall where they had the most consistent sampling. So the sampling goes very deep into the cave. And you can see that the deeper they go into the cave, the higher levels they get. And 700 meters into the cave, with a Draeger tube, he was measuring levels of carbon dioxide around 6%. And you can see up top that the level of oxygen was just below 15%. So if you add those two together, this comes out to a system that's 100% on that respiration line that Bill was seeing. You can see other times of the year, the black dots were in March after winter, cooler time of period, respiration being suppressed. CO2 levels were significantly lower and oxygen levels higher in the caves. So it's the kind of stuff Bill did. I corresponded with him recently, trying to talk him into publishing some of the stuff he's got. He's got lots of data. Another guy we mentioned earlier is an Australian caver named Gary Smith. And back in the 90s and early 2000s, Gary, who is independent caver and independent researcher from New South Wales, wrote a bunch of stuff. Here's a few of the titles for you on, which are great titles, right? On cave foul layer in caves, they call it foul layer in Australia. And so he's got some interesting stuff and takes you on a deep dive in from the Australian perspective in the work he did. But again, a lot of interest there in the carbon dioxide and how people react. Um, so we've started doing a little bit of work in Virginia. The talk was already long. We didn't want to go cave by cave in Virginia, or we'd be here till midnight, or at least a few of us would. And what you can see here, this is just a scatter plot of the values we've measured over the last couple of years in Virginia. It's about 150 points on there. And what you can see is that we've measured values up to 5% in Virginia caves. Some well-known caves we'll see in a minute that people never thought were had CO2 problems. We discovered actually did. And you can see a little bit of a reflection here, the seasonal pattern. That's a lot like what you see in Texas, which is in the late summer, early fall, the problem's worse. And then later in the year, it gets better. We have a lack of sampling points in January and February because we're usually counting bats and we forget to bring the CO2 meter. So Madison Saltpeter Cave, which probably I know several of you have been in who are here tonight in attendance. Um, in the mid 2010s, Bill Balfour and I were in there, and we were wondering why you always huffed and puffed coming up the hill from the lake. And he had a carbide lamp with him that day, and as we walked down towards the East Lake, the flame on the carbide lamp just started extending and extending and extending. We said, I think we have a bad air situation here. There was no record of it being reported. And we've measured, that's not the highest value we've measured. That just represents one measuring point. We've measured values over 3% at each of the lakes in Madison Saltpeter Cave. But again, when we have the O2 meter there, it doesn't look like the signal you'd expect from degassing or from allogenic CO2. It looks like the water is more acting as a sink trap. And I had always thought that it was degassing there at those lakes, but it doesn't look like it from the concentrations. Another cave, this is the one that's got the Virginia record right now. It's called Brother Dave's Cave near Front Royal, Virginia. And it has this little near sump that you have to go through to get back to where the monitoring point is. So between this little nasty place and Epiphryatic Lake, where we were doing some biological work, there's a tube about 100 feet long, and the CO2 in there can get up to over 5%. Okay.
Oh, well, that's it. We'd like to thank again, we've mentioned a lot of these people, but again, thank Dan Breaker and Natasha at University of Texas. And then DJ Walker is the coordinator for NCRC South Central Region, but also all the people who have helped us down there. Colorado Bend State Park has a lot of the NCRC stuff we do at the park there. Jeff and Heather Nichols Outdoor Adventures, they helped us a lot. And also, while participating with NCRC down there, they were helping us. Our rescue squad, Blacksburg Volunteer Rescue Squad, has been very supportive with some of this work, and also the Virginia DCR Natural Heritage Program.